Hello everyone for this new series of SIPTA seminars for the year 2024 and 2025. And we are quite happy today to hear the latest work on preference learning from Alessio. Without further ado, I hand over the mics to Alessandro, that knows very well Alessio, and that will introduce him and the seminar. So Alessandro, you're up.
Okay. Thank you, Sebastian. Hello, everyone. For me, it's a really big pleasure to introduce Alessio. Of course, Professor Alessio Benavoli, Associate Professor in Statistics at Trinity College in Dublin. I think to be Professor in Statistics at Trinity College fits very well Alessio's profile. Alessio is very much a statistician, in a sense, very much a Bayesian statistician. Maybe he will tell you, but I think this is very fitting. But in another sense, Alessio is much more than that. His research interests are very broad. I could say a lot formal about Alessio, but let me be a bit more informal, as I had the pleasure to be a colleague of Alessio at Tizia here in Lugano for almost 10 years. Not only colleague, we share together the office also with other people. Some people is related to this community. We were all part of the group of Marco Zaffalon. I was there in the same office with Cassio De Campos, Denis Mawa, Giorgio Corani was still with me, Francesca Mangeli was still with me. Let me say that all our desks were always very, very messy. We had a big office and all the desks were a mess. The people from the cleaning service were complaining a lot, but Alessio, in a sense, was the champion of the mess. His desk was always super crowded, but not in a static sense. His desk was always changing the level of crowd and the quality of the crowd. For instance, I remember when he started to get interested in quantum physics, he started to collect a few books on quantum physics. There's this one book, too big book, 20 books on quantum physics. And at some point, I think he really digested quantum physics and started to write something original about the foundation of quantum physics, the connection with probability theory from a Bayesian perspective. This was a phase before there was a phase of hypothesis testing, and he did a lot. Of course, the desk was crowded with different books. And this is just to say that Alessio really had a lot of research interest, very broad, but in a sense, he was always very, very deep in these different fields. And it's something you can see also from his CV, because it started in the Faculty of Computer and Control Engineering in Florence, where he got a master and a PhD. For a while, he moved also to work for a non-academic, I think still a research related, but non-academic field for like 2 years. And this is, I think, is something you can see also in his researches. There are many also applied. This is either theoretical and applied. Then he moved to Tizia, where he spent almost 10 years. Eventually was appointed the professor. And then he moved to Ireland, where he was in the University of Limerick, and finally in TCD, in Trinity College of Dublin. I just wanted to suggest you to read Alessio's paper, all the papers, but also to pay attention to what are the very last paper, because I think Alessio is very good in finding new direction for research. And if you have the chance at some point to talk with him, I remember I got so many different inputs from him. So I think you will definitely enjoy this talk. That's it. So let's give the floor to Alessio. And I will be chairing, but will be. And as you know, I think you have a bit more than 45 minutes, and then we move to the question time. Okay.
Alessandro, thank you for this great introduction. You cannot see my desk, but it's still very messy. I had to actually not to clean a bit because there was no space to keep my computer there. So not this change. Okay, so thank you for the introduction, and good afternoon, everyone. So the talk is about learning from preferences and choice functions. And sorry, okay. So just to give you a bit of background, this seminar is based on a tutorial paper that we recently published, I and Dario Azimonti from ITSIA. And you can find it in archive. This tutorial includes basically an overview of the problem of learning from preference and choices, but also includes a lot of examples. And more important is it took a lot to do that, basically a library, software library that you can really use to learn from preference and choices. So this tutorial is based on our research, but also the research of many people. And I want to mention Ike Ullemeyer, that is part of this community. He has done a lot of research on preference learning, and he also gave a SIPTA seminar before me a few months ago. Okay, so what is a bit of the outline of this seminar? You can see the topics I'm going to touch here. So learning from preferences is also nowadays called the learning from human feedback. That is a bit more fancy. And you can see the topics. Maybe some of these models, some of these keywords. So I'm going to basically present them, and I will mainly focus on object preference and choice function in this talk. Okay, so what are preferences? So preferences, I will say, are everywhere. And so we distinguish basically two types of preferences. What they are called observed preferences. For instance, when you do star rating, this is an observed preference where you express your preference with this star rating. Or maybe when you say, I prefer, I don't know, this laptop to this one. Okay, so these are observed preferences. But there are many cases where we only observe your choices. For instance, when you are on Netflix, you click a movie, you are not expressing a preference directly, but just your choice. But indirectly, you are saying that you prefer that movie to all the other movies you haven't seen in this platform. Okay, so sometimes you have choice, but this choice are somehow related to your preferences. And there are other cases where you can also have preference, for instance, in sport, where you have two players like tennis. So the result of a tennis match you can interpret as a preference of the winner player with respect to the loser player. So this model can also be used to, let's say, study tennis matches. I want to mention nowadays a very important application of preference learning that comes in large language models. So if you use ChatGPT often, you see that sometimes when you write a question, the software returns two answers, and then it asks you to click the one that you prefer. Okay, so this is an observed preference. It's really you are saying that you prefer this to this. And these type of preference data are used today to improve what is called fine-tune this model in a way that they return answers that are more meaningful to you, they are more useful to you. And so this is nowadays it's become a very important application of preference learning. Okay, so it's an overview. So I want just to start defining the concepts that you saw before in the outline. So what is object preference? Okay, so I'll start with this. So object preference is a preference over object. Okay, so what does it mean? So we have some objects like laptops. So let's assume we have M laptops, and denote each laptop as K. Each laptop has a vector of characteristics. For instance, you can see processor, generation, and so this orange column. And I assume that this vector of characteristics can be written as a vector xk in some in RQ, where Q is the number of characteristics. Okay, so for each object we have a vector of characteristics, real vector. And so when you say that you prefer laptop I to laptop J, I'm going to denote the preference with this symbol. It means basically indirectly that you prefer the characteristics of laptop I with respect to the characteristics of a laptop J. Okay, so this is what we mean with object preference. Is a preference over the characteristics of objects. You can do the same, for instance, with cupcakes. In this case, the vector of characteristics is the recipe. Okay, so I'm going to call the vector of characteristics the recipe just for short. Okay, and it's going to hold both for laptops and cupcakes. Okay, so this is one type of preference called object preference. There is another type that is label preference. Okay, the typical example is Netflix. So when you are in this platform and you choose a movie, you are expressing a preference over objects. Okay, so each movie has its recipe, like the actor, the director, and so on. Okay, so you are expressing a preference over objects, over the characteristics of the movies. But for Netflix, this is not the kind of preference they're interested in. So they're interested in the object. In Netflix, it's you. Okay, so in Netflix, there are instances that are in general people. Okay, each one coming with its own vector of characteristics, let's say, age, gender, and so on. So you have M people, M users. Then they have a set of labels, Y1, YL. These are the movies. They can take the titles of the movies. And so when the preference in this case is that the user with characteristics xk said that prefer movie yi with respect to movie yj. Okay, so this is called a label preference. It's a preference over label, but is in somehow annotated by the characteristic of the users. And in practical, the object in this case is the user. Okay, and they care about this because the idea that there is a user that is similar to you, so same age, same gender. The idea that is probably is going to like the same movies as you, and so they use your preference to suggest movie to new users. Okay, so the difference between object and label preference is really a matter of perspective. Okay, so depending on what is really the object. So in this case, I'm going just to focus on object preference, but the techniques that you use for object preference, you can also apply to label preference. Okay, so this is big distinction, but it's more like matter of perspective, that a mathematical difference in the models that we are going to use. Okay, but first of all, what is a preference? So in this talk, I'm going to talk about strict preferences, and they are preferences that satisfy these two properties. Okay, so a preference is a binary relation that satisfies this property. One is asymmetry, and it means that if you say that the pink cupcake is better than the white one, then you cannot say that the white is better than the pink. The other property is called the negative transitivity. Maybe you haven't seen this, but it's somehow related to transitivity. And it says that if the pink is better than the white, then for any, let me say brown cupcake, there are basically three cases. Either the pink is better than the brown, or the brown is better than the white, or both. Okay, so if a strict preference satisfies these two properties, we say that it's consistent, and the person that states this preference is said to be rational. Okay, so we are going to use these definitions. So you may wonder, why am I assuming these properties? Just because I wanted to have two properties, but I can also make these two properties imply, for instance, transitivity and completeness. So later on, we will see that we will relax completeness and have something more, let's say, similar to what we do in imprecise probability. Okay, but for the moment, I'm assuming this. And so this is what I mean with preference. And okay, so what we want to do is to learn from preference. And to learn from preference, we need a way to represent preference. So there are two ways we can use. Okay, the first one is through utility representation. So the idea basically is the following: that if you say that if you state a preference, this preference is consistent, so it satisfies asymmetry and negative transitivity, then this theorem tells us that there is a utility function that represents the preference and vice versa. So what does it mean? This that if you say that the object I is better than the object j, it means that in your head there is a utility function, for instance, taste, okay, such that the taste of object I is for you better than the taste of object j, okay. And what we are going to do now is, so learning from preference will equivalent to learn this utility function. Okay, this is what we are going to do. What we wanted to basically clarify that this utility function can be positive or negative. So what it is important that higher utility means better in terms of preference. Okay, so this can be positive or negative. Okay, so this is one way. There is another way to represent preferences that is called the two-argument function representation, and it basically say that if for you the object I is better than object J, then I can, this is a binary relation, I can represent this with a function that has two arguments. And then if you say xi better than xj, it means that this function is strictly greater than 0. Okay, so this approach, you can find this approach for each in Fishbone, and it was used to model intransitive preferences. So, but the idea, so what is the meaning of this Q? This Q you can think about as the strength of this preference relation. When this function is close to 0, it means that your preference of I over j is small. When this function is much bigger than 0, it means that you prefer xi over xj a lot more. Okay, so I'm not going to talk about this, but this is important because it's the favorite way to represent preference in machine learning, because it allows to transform the preference learning problem into a classification problem. Okay, so the idea here is that when Q is positive, means that xi is better than xj. When this Q xi is negative, means that the other side holds. And so it's a binary case, positive or negative, and so I can represent preference learning into a classification problem. I'm not going to discuss about this approach, but you can find this in the tutorial. I will go back to the utility approach that is better than the approach that I prefer. But yeah, you can find this approach also in the tutorial page. Okay, so what is preference learning? So we introduced the concept. So let me state exactly what preference learning is with an example. So assume that you are telling me that, so we have a cupcake, and I'm going to, with a recipe, and the only thing that I'm going to change here is the amount of sugar. Okay, so let's assume that this cupcake has 4.5, in some scale, sugar. You tell me that this one is better than the cupcake that has the same recipe, but with 6 of sugar. Okay, so you express this preference. So what does it mean? So we have seen from the previous theorem that it means that in your head, you have a utility function, and the utility function computed at 4.5, this value here, is bigger than utility at 6. Okay, this is why you are telling me that you prefer this to this. Okay, so we have this is the utility function over the recipe. The only thing that I'm changing here is sugar. And it is in your head. No, I don't know this function. Maybe you don't know this function, but you use it indirectly to express these preferences. So the goal of preference learning is given example of preferences, like this cupcake with this amount of sugar better than this one, is better than this. The goal is to learn your utility over sugar. Okay, so we don't observe this blue function, we only observe these preferences. Okay, this is an example with the recipe of one ingredient, but I can generalize over the case I change both sugar and butter. Your utility in your head is going to be a function of sugar and butter, and then you give me preference for cupcake that differ in the amount of sugar and butter, and I want to use this preference to learn this function of sugar and butter. Okay, so I will just focus on the sugar example just to make the things simple, but basically the approach is that we can use also not to learn a function of an ingredient, not just one ingredient, sugar. Okay, so this is, so to summarize, this is the problem of object preference learning. So we have like you set some preference stated by some person about a recipe of cupcakes, for instance. So this preference over the recipe. So the goal of preference learning is to learn that utility function and use the utility function to predict the preference of the user. So will the user like the cupcake with recipe x2 over the one with the recipe X3. So this prediction is important because I can use to basically, for a recommendation system. So I can, for instance, recommend you the cupcake that I'm sure you are going to prefer with respect to the cupcake X3, for instance. Okay, so this is basically the problem that recommendation systems need to solve. Like when Amazon proposes you a new object to buy, they use basically your preference to in somehow suggest a product. Okay, so how do we solve this problem? Again, there is huge literature about this, and there are many approaches. And just summarize 3 of them. This is not a complete list. So the idea is the following. So we have seen from the Brute theorem that if we have a consistent preference over recipe of objects, it means that in your head there is a utility function such that if you say that this is better than this, then the utility of that object minus the utility of this object is strictly greater than 0. Right? So we know this. And so the idea that to learn from preference, we can learn the utility function, and our evidence are these constraints. Okay, so use a function of the ingredient. So to learn this function of ingredient, on statistics, I can use different methods. So I can, for instance, assume that my utility function is linear. The ingredient, remember, the ingredient is a vector over RQ, the Q ingredients. So I can assume that my utility is a linear function with some weights, parameters that I don't know I want to learn. And so this is simply a linear function of X. So this is an approach. Another approach that, okay, maybe it's not linear, but it's log linear, okay? And so I can use this, and try to learn my utility function. For instance, if you go back to this case here, to this utility, it doesn't fit both those categories, okay? So we cannot use those 2 models. And so the idea that we may want to use a nonlinear model, so we, for instance, a neural network where we define some basis function that are nonlinear instead of X. We have nonlinear function of X, maybe depend on some parameters, and we want to use this to learn the utility function. Okay, so these are the 3 main approaches, but they have basically drawbacks. Okay, so the drawback here is, okay, this assumption they are too narrow for general utility functions, and the problem with this, the nonlinear approach, the neural network approach, in principle, may learn any nonlinear function, is that it tends to have a lot of parameters. Okay, so if you want to learn nonlinear function, a bit complex, this is going to have a lot of parameters. So you need a lot of data to learn these parameters. And in object preference, so preference coming from a person, usually the number of preferences you have is small. Can be 10, can be 20. Difficult. It's very difficult to exceed 100. Okay, so it means that it's difficult to learn a lot of parameters with such a small data set. So another drawback of this approach that there is no representation of uncertainty. As I will see in a second, representation of uncertainty is very important in recommendation system. So if you want to recommend something, you need to know the uncertainty. Okay, so how do we solve this problem? And this is basically my research on this is to use Gaussian processes. Okay, so I'm going to explain what Gaussian processes are in a second, but let me again state the problem. So we have some preference over object. These preferences are constraints the utility over the object with these constraints. So I'm going to basically introduce a bit of notation. So let's imagine that you have tried are different cupcakes differing the recipe. So this is the set of all the recipe, the cupcakes you have tried. And so the thing that I don't know is your utility over these recipes. Okay, so I'm going to denote this vector of R scalars, okay, as U capital X. And so what it means that I can represent these constraints in this matrix form. Okay, so it's a way to represent this constraint in a more compact way. So basically it means that when you state preference, you are constraining the utility in a linear way, and you can see that linear constraint. So it's linear constraint over the U, okay, so over the value of the utilities. So stating preference is equal to constraining indirectly the utility, and so we can use this as a likelihood to build a probabilistic model to learn this vector of utility. So these are the unknown. Okay, so our goal is, given the preference, we want to learn these utility functions. And once we have learned U, we can use U to make a recommendation. Okay, so how do we do that? By defining a probabilistic model. Okay, so first we define a likelihood, so the probability of the data, the preference with respect to the unknowns. The unknowns are the utilities over the recipe of the objects. So what is the likelihood? The likelihood is very simple. It's 1, it's an indicator function. So it's 1 if the vector of unknown satisfy the constraints, or 0 otherwise. Okay, so basically, if the utility is compatible with the constraints, the indicator is 1, otherwise is 0. Okay, so the unknown here, it's a function, utility, and as a prior of a function, I'm going to put a Gaussian process. I'm going to explain in a second what a Gaussian process is, but you can think as a multivariate normal distribution, and the reason is in the next slide. Okay, so I have my likelihood, I have a multivariate normal. I want to compute the posterior. Okay, and the posterior, it's very simple. It's a truncated normal. Okay, so it's the normal truncated here. Okay, so I have truncated normal over a high-dimensional object. I can have R, different cupcake. R can be 30, can be 50, depending the cupcakes you have tried. So this is your posterior. And once we have this posterior, I can basically use it to infer the value of utilities for recipes of cupcakes you haven't tried. Okay, so I want to know what is the utility of the recipe of a new cupcake given the data. Okay, and I can do by doing this prediction model. It's very simple to do because this conditional, it's a multivariate Gaussian, comes from this. And so basically I need to solve this integral, and I can do by sampling from this truncated normal, sampling from multivariate truncated normal. It's doable. There are efficient way to sample from this. So I can basically solve this integral by sampling. Okay, so I have my probability. I can use this probability to understand if you will like or not a cupcake, with, or better, you will prefer or not a cupcake with a recipe, X star. So this is the model we are going to use. And the thing that you need to understand is the prior, that is this Gaussian process. Okay, so what is a Gaussian process? So a Gaussian process is a prior of a function. Okay, so what does it mean, a prior of a function? It means the following. So a Gaussian process is defined in the following way. So imagine you have a function like that. Okay, and you select some point, x1, x2, x3, x4, x5, and then you take, the value of the function at that point. So we have, this vector of values. Each one is a real number because the utility function is a real function. So we have 5 numbers, vector of 5. So a Gaussian process basically it's a prior over function such that when you choose n values of the function, in this case 5, okay, you get a marginal that is a multivariate normal distribution with a mean that is this vector finite number. So the mean is defined by the mean function of the Gaussian process. There's a function you have to specify, the parameter of this Gaussian process. In this case, you have this vector of 5 numbers and a covariance. So you have a k, x1, x1, so the covariance with respect to all the x's, and that depends on this covariance function that you have to choose. So basically, a Gaussian process is a process whose marginals are multivariate normal distribution. Right? And so to define it, you have to define a mean function and this covariance function. Okay, so for instance, the mean function, as you will see, we can choose the 0 function. So it will be always a vector of 0. And what is important in the Gaussian process is this covariance function. Okay, so why? because it determines basically the correlation between values of the function at different axes. Okay, so a typical covariance function is this one that is called the square exponential kernel. It's defined over vector of x, or recipe, more few ingredients, or better, C ingredients, and it's defined in this way. So this basically what it does is basically says that the correlation between value of the functions, okay, decay exponentially, like a Gaussian, okay, as a function of the distance between for instance, x1 and x5. If you stretch this, the correlation decays exponentially, like the tail of a Gaussian. Okay, so basically, to define a Gaussian process, you need to define this kernel. There are other type of kernels, but this one it's very nice because of this property that allows the Gaussian process to fit a very large class of functions. Okay, so it's very used. And the nice thing about all this model, this prior, that when you choose this covariance function, it has basically a number of parameters that is equal to the dimension of x. Okay, so in this case, since x is scalar, we have only one parameter. Okay, so basically this model has the same parameter of like linear regression. Okay, but it can fit any nonlinear function. Okay, so this is the idea. So how do we do that? So okay, let's go back to this problem. So we have some preferences. We want to learn our utility over sugar, and we want, for instance, use it to predict if you are going to like a cupcake with sugar 5 or a cupcake with sugar 6. Okay, how do we do that with that model? So we start with our prior. Okay, that is this Gaussian process, and since it is a prior function, I can sample, okay, from this prior. So here you see I chose a Gaussian process with mean 0. The mean is this black line, okay? And I can sample function from this process because basically I can use the previous representation to sample function from this process. And I can use these samples to answer the question, is U5 greater than U6? Okay, so how do I do that? I go at 5 for each sample. I consider its utility at 5. So it is U5. Go at 6, U6, and I compute this difference, U5 minus U6. In this case, this is negative. Okay, I can do this for each sample, and I can do a density plot, okay, of these differences of U5 minus U6. This is what you see here. And you can see that this is plot at the beginning is like symmetric around 0. So it means that at the beginning, the model assign a probability of U5 being better than U6 like 0.5. So I am like assuming that the user is indifferent between the two cupcakes. Okay, that's why basically so this is before having any data. Okay, so we have this model, and down let's assume we just have one preference. Okay, so you tell me that you prefer the cupcake with sugar 4.5 over 2. So in this case, I take that prior, and my likelihood is this. I get a truncated posterior, and I can sample for it. And this is, you see the sample. The mean of this posterior is not anymore 0. This black function here. And now, basically, for all the samples that you see here, what we have that the utility at 4.5, so this one, is bigger than the utility at 2. Okay, so the samples, here, the samples are consistent with your preference. Okay? And I can use, again, the samples to answer this question. Do you prefer cupcake with 5 or over cupcake with 6 sugar? And you see in this case, maybe probably is a big higher for 5 over 6. Right? So this is nice because I have an uncertainty, and I can basically, if I need to do a recommendation, I can use uncertainty to make this recommendation. And then you can see what happened after 2 preferences. The model adapts, includes, so you learn a bit more about 5 over 6. And if I use, in this case, 5 preferences, basically the model, in this case, fully sure that you're going to prefer 5/6. Okay, so, and you can see that the shape of the function starts to resemble the utility that the user is having in their mind, and what I'm using to generate these preferences. Okay, so this idea of preference learning with Gaussian process. So remember, in this case, we have only one parameter, and with one parameter we can learn a nonlinear function. Okay, and a representation of uncertainty that we can use to make a recommendation. With only basically five examples. It's amazing. Okay, so what is the issue about this model? That if you know from psychology, from economics, peoples are often irrational. So it means their preferences are not going to be consistent. So they're going to violate asymmetry or negative transitivity. So what do we do in this case? So researchers said, okay, try different models to account for this irrationality, and we are going to see some of them. Okay, just to understand how we can change the previous model to account for this source of irrationality. Okay, so an example is what is called the limit of discernability. So what does it mean? This that if I give you, two cupcakes that we have similar amount of sugar, you may make a mistake in your preference if I force you to choose one. Now, if I force you to choose a cupcake, you may say that this is better than this, when instead, according to your utility, your mind, this should be better than this. Okay, but since you cannot distinguish the preference, you cannot distinguish the amount of sugar because it's too near, you cannot basically state the preference correctly. So it means that your preferences, when I ask many questions about cupcakes, may at the end violate asymmetry or negative transitivity or both. Right? Asymmetry can happen with what you call noise. So, for instance, when you prepare the cupcakes, maybe you think you're putting 3.1 sugar, instead at the end, for some errors, you put 3.6. Okay. And also, this is going to generate issue in your preference. How do we account for this? Okay, I will just focus on the limit of discernability, but we can use a similar model for this type of noise. So the idea is the following, So before, what the limit of discernability tells the following: that if we take the utility of two objects, so what we assume when the utility of these two objects it's very, very near, okay, because you cannot distinguish the two objects, then you will, let's assume when this goes to 0, okay, you basically say this or the other direction with probability 0.5. Okay, you cannot distinguish them, so you are going to choose one basically at random. Okay, and the idea that we can account for this model by basically replacing the indicator, so that strict inequality, with a soft indicator. So for instance, the CDF of a Gaussian distribution, the shape. And we know that this, when the difference is 0, is equal to 0.5. Okay, and introduce a parameter that is called the discernability parameters, such that when this quantity goes to 0, okay, then this function is going to become like an indicator function, and we are back to the previous case. Okay, when this is big, this is going to be more flat, and so it means that you will be able to distinguish cupcakes that have some different utility, but you still be able not to make a mistake. Right? So this is the idea. So we replace an indicator with a sigmoid function. The likelihood, instead of being an indicator, become a multivariate CDF. In this case, if I use this sigmoid function of that constraint, when again sigma goes to 0, I get back to the previous model. And the idea that now I'm going to learn sigma from the data in a way that something like I'm trying to learn your limit of discernability. Okay, so if you are good, you can distinguish cupcakes that are very similar. The sigma for you will be small. If you have a cold, for instance, you cannot distinguish much, then the sigma will be big. Okay, so this is the model, and I think that we can change the likelihood. We keep the same prior, the Gaussian prior. The posterior, is what we proved in this paper, is actually a skew-normal distribution. So it's a normal that is asymmetric. I'm going into detail, but basically we can compute its own parameters. We can sample from it, and so we can basically do similar things as the previous model. So we can learn a utility assuming that the user makes mistakes, okay, when setting the preferences. And for instance, for the case we have seen before with those 5 preferences, now basically when the small sigma is different from 0, we see that the model is more uncertain. So in this case, we are not saying with certainty that U5 is better than U6, but there is an uncertainty, and this uncertainty comes from the fact that the user has a limit of discernability. Okay? And so in this way, we can make basically this model robust to violation of asymmetry or negative transitivity. Okay, so this is one. So there are other cases, the user may be inconsistent. You can see here another example that is time. So the preference may change with time. Okay, so I'm not going to discuss this because it's a problem. It's very vast. Okay, but the idea that in some cases we can correct account for the depends on preference over time by having a utility that depends on the recipe of the object, but also on time. Okay, and this way we can account maybe the fact that preference can change in time, so violating asymmetry, for instance, over time. Okay, so let me go to another example. So here we have seen an example of irrationality. Okay, so we wanted to somehow account the fact that the user may be irrational, okay, and fits the model. Sometimes we want to put more rationality in the model. Okay, so this is an example that, well, this is the case. So preference over flights. Okay, so I have flights from Dublin to New York. Let's say that the vector of the recipe in this case is the cost of the flight, the duration, the company, you see here, and the departure time. Okay, so this is my characteristic. And of course, what we want for this model, we want to satisfy additional constraints over our preference. So a very simple constraint that if I keep everything fixed and increase the cost, okay, then the flight should be worse than the previous one. Okay, the same for duration. So this is something that it's common sense. That this should be the case. So it means that our utility is going to satisfy this type of constraints. So the utility of cost plus a delta, some amount that is positive, is going to be less than the utility with the same cost. Assuming all the rest is the same. The same for duration. We want a shorter flight usually, and we won't have this type of constraint over, for instance, departure time. There is no reason to assume this constraint on departure time. Okay, so we want to assume this constraint to impose more rationality. How do we do that? But it's very simple with this Gaussian process because basically those type of constraints are derivative constraints. Okay, so for instance, over cost, I have my utility over cost. I wanted to impose the constraint, something that I know a priori in my model, the utility should be decreasing over cost. Okay, and the nice thing about the Gaussian process is that since this is a linear constraint over U, if U is Gaussian process distributed, also the derivative of U is Gaussian process distributed, and so I can basically use a theory, derivation similar to the one we have seen, to basically constrain my model to satisfy this constraint. Okay, so a priori, before this was our prior over the sugar, so something that could be positive or negative derivative over the amount of sugar. But now, if I constrain this prior with this, I get this. So a priori, my model is telling me that the derivative over cost is negative. Okay, so any flight with cost 0.8 is going to be worse than any flight with cost 0.4. Okay, so I can put this constraint in my model, and so can put more rationality in my model. Okay, and of course, just skip ahead with this, but a typical example where we use this type of constraint is desirable gamble. So when our object is a gamble, so what is a gamble? Imagine we have some we call it a random experiment, like we toss a coin, and so the result can be heads and tails. So a gamble, it's simply a bet on the results of this toss, where if we have heads, we get $2, and if we have a tails, we lose $1. And so a preference over gambles is a preference over the characteristics of the gambles that are, in this case, 2 minus 1. So the amount we save for heads and the amount we save or pay for tails. So we are placing preference over these vectors. And so this preference constrains the utility that we have. Okay. But of course, in this case, we want to impose monotonicity constraint with respect to both the component. And why? Because if I have a bet and I add a positive constant both on the top and the second element, I got something that is better than this bet, because I will get more money. So I want to impose in this case that my utility to be positive derivative with respect to both the components. Okay, and so the idea is I can constrain my Gaussian process a priori to satisfy this constraint, and I can give an example of preferences, okay, and use this preference to learn U with this constraint. Okay, so this will be like learning nonlinear utility over preference over gambles, assuming that this monotonicity constraint is satisfied. Of course, this is not desirability. If I want to get desirability, so standard one, I need to make a further assumption that my utility is linear in the recipe of the gamble, this object here, okay? And if I do this, I can still use the Gaussian process to model this case, because basically I can represent this function with a Gaussian process with this covariance function. Okay, so I can still use that theory to learn a linear utility, but I can do more general model that learn nonlinear utility with this monotonic constraint. Okay, so let me move to choice function. So okay, so there are another sorts of irrationality over preferences that are cases where, for instance, this, so where we have a laptop and you say that this is better than this because of the CPU, for instance, this is better than this because of drive, and this is better than this again because of CPU. So this preference may violate transitivity, but it's because you have multiple utilities in your head. Okay, so this is the case. We have multiple utilities. How can we learn from multiple utilities? So nicer way is to go towards a more general model and to account for the fact that when you have multiple utilities, there may be objects that you cannot compare. So we have what we call incompleteness. And so means that in this case, you say these objects are incomparable because one is better with respect to utility 1 and the other with respect to utility 2. And so, for instance, we may choose both. Okay, so this is what choice function are. So we have a set of objects, cupcakes, and we choose some objects because we think these objects are better than the others that we discarded. And these two somehow are incomparable, okay, in some sense, to be defined. Okay, so can we learn choice function? Okay, so can we learn this type of choice function? So basically, I have this kind of data. They're not anymore preferences, are choices, like this you see here. I want to learn from these choices. I want to use my model to predict choices, your choices with respect to another pool of options. How can we do that? So we can use the same similar approach. We can assume some rationality criteria in the way, or consistency criteria in the way people make choices. These are famous one. For instance, Chernoff one says that to assume that in this case you selected these two cupcakes, and then I said to you, I'm sorry, today we don't have this cupcake. It's finished. And then you say, okay, no, in this case, since you don't have that, then I select this and this. Okay, so this will be like irrational because you had this option before. Okay, so nothing changed. So I removed something that you didn't choose, so you should not change your choice. Okay, so this is a form of rationality. And again, so we assume some of these rationality criteria that are similar to this. There is a utility representation. In this case, it means that in your head, you have multiple utilities that you use to make choices. For instance, a way to make choices, you choose each object that maximize at least one utility. So for instance, you assume that this utility for this object for you, it's, let me see this one, is better for other tastes, and this is better for visual appearance. Okay, so this is the way you make choice. Okay, so you choose the objects that are better with respect to at least one utility. So in IP, this is called the admissibility, just to give a reference. So can we learn from choice function? Yes, we can. And okay, so we can again embed the rationality constraints in the likelihood. In case we have L utilities, so more than one, and we can put priors over the utilities for each one, Gaussian process, and learn the posterior. Okay, so the model is slightly more complex to describe, but it's similar to the previous one. So in this case, we have multiple utilities, and we have indifference because we cannot choose one object with respect to the other because they have different, there is a trade-off in the utility, right? Okay, so preference learning. So I want just to finish with this example to give you an example of how we apply this learning from choices. This is an example we did with one student, just for exercise. So we show the students photos of ellipses, as you see here, and ask the student to choose the ellipses that the student prefer based on these two criteria. Okay, being closer to a circle and be aligned to the axis. Okay, so again, this is it's a choice function wherein somehow we give the utility to the student. Okay, our goal is basically not to use the choice of the student to learn back the utility. Okay, so in this example, the student selected this utility and this. Okay, so because this is aligned to the axis, I guess, and this is closer to being a circle, and so both the utility are better. Sorry, both the ellipses are better than this with respect to these criteria. Okay, so one is better with respect to the first one, and this is better with respect to the second one. Okay, so we did this. So we asked the students we took 15 images of ellipses. Each one, as you see, we reduced the resolution to make the problem a bit more difficult for the student. And we basically asked the student to generate choices for 160 examples. Each example is has 3 ellipses. Okay, so we had 160 choices. And then, so then we trained the model for these choices, and we left some example out for testing. And so you can see here what actually the model returns. Okay, so you can see here the model is, in this case, the model is learning 2 utilities using only the choices of the student. And what the model returns is a posterior distribution over the value of the utilities for the 3 ellipses. Okay, so in this case, you can see for the utility 1, that we don't know what it is in the model say, okay, for this utility, the ellipse 21, so this one, okay, the ellipse 21, one at the right, is better, so has higher utility than the other 2. Okay, for this object, for this utility 2, okay, the ellipse 15, this one has higher utility than the other 2. Okay, so and basically the model in this case predicts perfectly the choice of the student, because the student is basically going to choose this one with respect to this utility, and this one with respect to this utility 2. Okay, so this is an example. Another example is okay, this case here where for both utility, the best is this, so almost a circle in this case. And so in this case, basically the model say, okay, the student is going to choose this because it's the best with respect to utility 1 and utility 2. Okay, so I can learn from choices. I can use then the model to predict choices of the student with respect, for instance, to even not to cases, ellipses that the students are seen. Okay, but we can do even better. No, we can make a program where we draw ellipses. Okay, and we try to find the parameter of the ellipses that we know the student will like the most. Okay, so in this case, with respect to criteria, the best ellipse will be like a circle. Okay, so we can manufacture the best list for the student. And just to finish, with actually an application of this model that we are basically using. So the idea basically is we can use this model to find the best recipe for objects. So basically to manufacture better objects. Okay, so you can think any manufacturing process. Any manufacturing process you can think being the same as manufacturing cupcakes. So you have the ingredient, you have some preparation procedure, some oven, some machine, that does something, and then you have the product. Okay, so now assume that we ask some user to rate the product, to say, okay, I prefer this to this. Okay, and now we want to use that preference to not only recommend a new cupcake, but really change the recipe, the preparation procedure of the manufacturing process to make a cupcake that we know the user will like the most. Okay, and we know that we can do with this model because the model can predict what the user is going to like. And why basically we test this in different applications. So you can see an application here where we use basically this model to improve the parameter of metal additive manufacturing. So it's a process where you use a 3D printer to print metal pieces. You can see here this machine, so everything happens inside here. And so this box machine works like that, and it deposits a layer of powder, metal powder. Okay, and then there is a laser that melts the metal powder layer by layer, and then at the end you get any shape that you want, like this. And so what we did basically, we used the choices over this object to find the parameter of this machine, so the power of the laser, the speed of the laser, and other parameters. In a way, we get the block of the object that was most preferred by the user, okay, according to some criteria that were defined by the user. Okay, so basically we can use those models to make objects, not only to predict the quality. Okay, so thank you. That this is just a bit of summary. So just to let you know that preferences are everywhere. So I just talk about preference, but there is other way we can give feedback. They are somehow all related to preferences, or at least we can see them in that way. And I want just to point out that what we did in that tutorial is to make a library to learn from preference choices, and you can use that library to make your own model. Okay, so you can change, for instance, the likelihood, make your own model, because as you can imagine, there are other models you can think about choices, about the rationality that I haven't touched in this talk, where there is no model yet. Okay, so thank you.